a high level section of the periodicity section. Transition elements, looking at their properties and talking about them having incomplete D sublevels. So this is what we need to know. They have variable oxidation states, or combining powers. They form complex ions with ligands, colored compounds, display, not display, catalytic and magnetic properties. And zinc isn't counted as a transition element because it doesn't have an ion with incomplete d orbitals. So if we look here, maybe we could expand on that point now. And here we go. So if we take a look at zinc atom would be argon, and then it's going to be 4s2 3d10. Now the only ion that zinc forms is Zn2+, doesn't form any other ions, and what that's going to involve is the loss of those, which means it doesn't have an ion with any, because this is full, doesn't have a partially filled D shell, and as a result we don't count zinc as a true transition metal. The other ones I've just highlighted here just for you to be careful of, just to flag up when they're talking about the electronic structure of the atoms. If you remember, there was some additional stability for the half-filled shell in chromium, so it exists like that, and there's also a little bit of additional stability for copper in terms of it having a full D shell like that. Okay, so just be careful of the two electron configurations and don't include this one in your definitions of transition metals. So the oxidation state, their charge, can vary. So if you take something like lithium, lithium is 1s2, 2s1. All that's ever going to do when it reacts is become 1s2. It's going to lose that 2s electron, and we end up with Li+. Nothing else. Don't see Li2+. That would be far too much energy to start on the next shell. However, with our transition metals, we've got a few more options open to us. If you maybe come across in the lab compounds like copper oxide. Here, they're both copper oxides. This is actually copper 2 oxide, and this is copper 1 oxide. So the oxygen's always going to be O2 minus. What I've got there with it is a Cu2 plus, and what I've got here with it are 2 lots of Cu plus. Okay, so it's able to be +1, +2. And so we make use of these Roman numerals to help us with that numbering, so we can talk about their oxidation state or combining powers we used to discuss, to see which one we're dealing with. So if this is iron 2 oxide, then it's iron 2 plus, oxygen still 2 minus. This one would be Fe2O3. So we've got 2 lots of Fe3 plus 3 lots of O2 minus. Overall, that ionic compound then has a neutral charge. Why is it able to do this? Well, it goes down to the ionization energies really. If we're thinking of what's this 182, 281, that's sodium. Sorry, if we talk about sodium, it loses that 1 electron, and then we've got quite a jump to the next shell, and then there's our inner shell, so we don't really get enough energy to warrant this. Whereas with our transition elements, it's a much smaller change between our subsequent ionization energies, and as such, if we have differences in bonds being produced, if we have differences in hydration enthalpies, so if someone's got a bigger charge, you get more energy out when it dissolves in water. Small differences like that are able to accommodate losing more than 1 electron. Right, so we've got several different options open to us. And one of the other things that we're going to talk about with our transition metals is that they form these complex ions. So if we've got that charged metal ion, we find that we get these ligands that are able to form dative covalent bonds to it. So in here, in a ligand must have a lone pair of electrons. So here are the ligands in this molecule, and that lone pair of electrons is being donated in to an empty d orbital on our central metal ion. So we call these dative covalent bonds. When you get onto your acids unit, you'll learn that this is a Lewis acid and these are Lewis bases. But we've got a nice octahedral shape here with these 6 ligands sitting around the central metal ion. And we describe this whole thing as the coordination sphere, so its coordination number is 6. And very often these are coloured, and we'll talk about that in the next section. Something else we find as well is that ligands that bind more strongly will kick out ligands that bind less strongly, right? So we can get ligand substitution reactions, ligand exchange. Now ligands can also be charged, so Cn minus, there's a lone pair on that C that again can donate in, but this time we've got a negative charge, and that then comes into play when we think about, well, what's the charge on the overall species, overall complex ion. So because the Cl, if I take this one as an example, because Cl is a negatively charged ligand, Cl minus, what I've got here is I've got a Cu, I've got 4 lots of -1, and overall that's equal to a total charge of -2, which means my copper must be +2, solving that equation. And you can do that for these other ones. This is going to be, if you pause it, this is going to be +3, this one is going to be +7. Over here, this one is going to be +1, because this is a neutral ligand, that's -1. Take that, oh no, my mistake, sorry, it's going to be +3. Take that over, it becomes +3. And this one, as it's written, I don't think you can tell. Right, so some ligands. We talked about ligands on the other page. We had ammonia and water as examples there. These are some from the data book, slightly more unusual in that they are the bidentate or polydentate, which means dentate can you think of biting. So if we look at our 1,2-ethanediamine here, you can see this lone pairs on both of it, and that could form 2 dative covalent bonds. This one potentially could form several more than that, could form 4, and this one could also form a couple as well. So if we've got our lone pairs, we can get more than one dative covalent bond coming out of our ligand. Now, because ligands are able to show variable oxidation states, then they're also making good catalysts, because they can flip through those oxidation states and help speed up reactions without themselves being used up in the process. And you can see here a chart for P450 enzyme, which is a biological system that oxidizes substances. And you can see it involves iron, and the iron's flipping between a few of its oxidation states to facilitate this process. You can see there's the iron in a heme ring. You can see the dative covalent bonds as it sits there in its plane. Now, 2 terms just to highlight: homogeneous, heterogeneous. Homogeneous is where we have our catalyst in the same phase as the reactants. Heterogeneous is where it is in a different phase. So this example here in the body would be homogeneous. Heterogeneous would be something like your solid platinum, palladium in your catalytic converters, or some solid iron in the Haber process, which uses gases as well, so it's in a different phase. Magnetism, we also need to just talk about this as a final point. So when you've got a spinning charged electron, it has its own sort of magnetic field associated with it. Now, everything has a degree of diamagnetism, and that produces a weak opposition to a magnetic field. So everything has electrons moving around in their orbits, and that makes them diamagnetic. Paramagnetic is where we have unpaired electrons. So if we've got more electrons pointing in a particular direction, spinning in a similar direction, then we have paramagnetism. It's a little bit stronger than diamagnetism, and it would attract them to a magnetic field. So we can, there's devices that you'll maybe see in your textbook where you can, it's almost as if you're weighing them, you put them in a magnetic field and you see which way they move to decide whether they're diamagnetic or paramagnetic. The strongest one though, ferromagnetism, where we end up with long-range ordering of unpaired electrons. So if you start off with a lump of iron, you've got lots of, you can see this, electron domains all pointing in different directions. if you expose them to a field, you can get them all to line up, and that lineup remains after you take the field away as well. So it remains magnetic. So if you stroke a piece of iron with a magnet, you will induce these similar directioning of the electrons, and you can make that piece of iron magnetic. Right, that's what we've covered. Same typo again, and there's a couple of other places I got some images from.